Hello everyone, my name is Victoria and I'm a graduate research assistant at Florida International University, and today I will be presenting the work titled AI-driven malware defense, a transformer model for real-time detection and threat analysis. Here's the structure of today's talk. First, we'll discuss the limitation of traditional malware detection and introduce our proposed system. Then I'll summarize the key contributions of our work, walk through the dataset and pre-processing pipeline, and explain the transformer architecture. After that, we'll look at model performance, real-time explainability, zero-day evaluation, and finally conclude with future research directions. Modern malware evolves rapidly. Attackers use evasion, polymorphism, and obfuscation to bypass signature-based detection. Traditional antivirus tools depend on known byte patterns, which means they often fail against zero malware or threats that change rapidly. Machine learning helps address these weaknesses by learning behavioral patterns rather than relying on signature-based detection. In particular, transformer models are very effective because self-attention can capture long-range dependencies in behavior logs, especially API call sequences. However, challenges still remain, including interpretability and robustness against new or unseen malware families. To address these issues, our proposed system combines a transformer-based detection model, real-time explainability, and zero-day detection evaluation. Speaking about these contributions, we have a transformer-based detection framework that is trained with API call sequences extracted from portable executable files. A human-centered explanation module uses gradient-based attribution to highlight the most important API calls. A GPT-based explanation generator translates the token into short descriptions. A gradient interface displays predictions, confidence scores, and highlighted features. Finally, we test generalization by removing entire malware families during training. Our dataset consists of about 60,000 JSON reports generated by the Speakeasy sandbox. Each report includes mostly API calls, but also file paths and network activity. These features are truncated and padded to a uniform length of 512 tokens with a vocabulary of 3,274 unique tokens. This is a binary classification task, and five-fold cross-validation is used, together with a batch size of 32 and early stopping. The training was conducted on a workstation with an Intel Core i9 32GB RAM. Training takes about 2 hours per fault, and in total roughly 10 hours. The pre-processing pipeline has two main stages. First, we focus on behavioral attributes and remove noise such as control characters and execution-specific details. We extract API names and types, file operations, and network or port usage. Everything is lowercase and separated with standard white space. In the following, we apply a white space-based tokenizer. Tokens are mapped to a vocabulary index where unseen tokens become unknown and short sequences are padded. The result is a consistent PT tensor for each sample ready for model training. During the transformer phase, API tokens are converted into dense vectors. Positional encoding are added so the model can understand order. There are two transformer encoder layers. Each layer includes multi-head self-attention, residual connections, layer normalization, feed-forward networks. Self-attention lets the model learn global behavioral relationships across an entire API call sequence. After the encoder layers, we use min pooling to create a single representation which feeds into a classification head that outputs benign or malicious labels. The model shows smooth convergence during training, as both training and validation loss decrease without signs of overfitting. We achieve overall accuracy above 92%, strong performance across ransomware trojans, runs, droppers, and backdoors. Some lower accuracy for coin miners, keyloggers, and system Windows 64 processes due to smaller samples and heavier obfuscation. The false positive rate is low, and the model maintains high true positives and true negatives. Two factors help explain model behavior. First, the token frequency shows that certain API calls, for example, heap free, get module handle A, and virtual alloc serve as strong behavioral indicators. API sequences length vary across samples. Short sequences like behavioral information, making classification harder. Longer sequences contain richer behavioral patterns, which transformers handle effectively due to self-attention's ability to model long-range dependencies. We developed a Gradio interface that makes the system usable by analysts in real time. The interface lets user upload any JSON report, and after running the testing, it displays prediction, confidence, sequence length, percentage of unknown tokens, and highlights influential API calls based on gradient attribution. We then feed the highlighted tokens to GPT with fixed prompt asking why those API calls may be suspicious. In the example on the right, we see that local alloc API in malicious context can be used by malicious software to allocate memory for storing harmful payloads or to overwrite important system data. Inference is over 500 samples per second, and even full families can be processed in just a few seconds, making the system suitable for real-time detection. To simulate zero-day conditions, we remove entire malware families from the training set. Ransomware and keyloggers show low transferability, meaning they rely on unique behaviors not present in other families. Rats generalize very well, likely due to shared behaviors. These results highlight the importance of diverse and representative datasets when building zero-day resilient models. Key takeaways is that our transformer-based system achieves 92% accuracy. Explainability is a major strength, as gradient attribution and GPT-based explanation create transparency and trust. Real-time inference allows practical deployment in cybersecurity environments. Zero-day evaluation shows strong generalization for some families, but challenges remain for highly specialized malware. Future work aimed to improve detection of rare and highly invasive malware, enhance real-time performance further, explore hybrid models combining behavioral, static features, and memory analysis, continue advancing transformer-based cybersecurity approaches. Thank you for your attention. I'll be happy to take any questions on my email and let's stay connected.